He specializes in water quality and water management, and today we'll share certain aspects to consider when thinking about implementing tile drainage on your land. I'm going to hand it off to you, Dr. Helmers.
All right. Thanks so much, Laura. I'm excited to present today. Uh, I always get excited if I can talk about tile drainage, and I'm excited to share in this case, virtual stage with Margaret again, as we did at the conference in December. So I'm going to talk a little about tiling and water quality, and maybe how the two can go together. Laura, if you can just give me a thumbs up if you can hear me okay. Okay,
Looks great.
just want to
Yep.
make sure. So I'm going to touch on, um, start my timer, so make sure I don't take up too much time. We're going to talk a little about drain spacing, controlled drainage, bioreactors, saturated buffers, wetlands, drainage water recycling. Most of those just give a little snippet, and you're going to get to hear more about bioreactors from Margaret in her talk. So as we think about tile drainage, it's extensively used throughout the upper Midwest. Many positives associated with it from a crop production standpoint, but we do need to recognize that it's a delivery mechanism of nitrate nitrogen that moves below the plant root zone, uh, and it can deliver that nitrate nitrogen that's lost from the plant root zone to downstream water. So certainly throughout much of the upper Midwest, we're very concerned about that. Central Iowa, where I work, we're extremely concerned about it as we think about some of our drinking water supplies. There's can be a positive in for some precipitation events. We can see a decrease in surface runoff because we've allowed some of the water storage capacity kind of back in the soil by draining out some of the water and having a little water storage capacity for the next rainfall event. And so it can help reduce surface runoff for some of those. One of the things that maybe hasn't been thought of as much, but impacts on end management. And a colleague of mine here at Iowa State University, Dr. Mike Castellano, has been looking at this. And so he had a student that worked on this where we had some drainage plots, kind of relatively undrained plots, and then drained plots. And what we found was that drainage, as we would expect, it helped us increase crop yield. So, that would be something that farmers understand. But what we also found was that it helped increase agronomic efficiency, such that we were able to reduce kind of the agronomic optimum and fertilizer rate when we had a better drain system. So our drain system required less end inputs to get that agronomic optimum crop yield. So that was kind of a positive as we think about this. Is if you have a well-drained system, you may be able to think about a little more on your fertilizer rate, and perhaps back that off a little bit where we have good drainage systems. So I think that's another positive we have not thought about as much as you start looking in the drainage literature. So as we think about drainage, maybe one of the take-home things I would say for me today would be um, to kind of understand drainage coefficient. Drainage coefficient, if you talk to drainage folks, be something that they talk about quite a bit. The drainage coefficient would be the amount of water that can be removed in a 24-hour period from our field with our drainage systems. Modern design standards would call for about 3/8 to 1/2 inch a day. So we would like to be able to remove that much water in a 24-hour period from our crop field. Now, that is, as we think about it, the drainable porosity of the soil might be about 4 to 5%. So if we drained a 1/2 inch of water in a 24-hour period, that may drop the water table about 12 inches. That would allow air to get back in those soils so that we have less chance of having any negative impact on our crop production. So that 3/8 to a half, 3/8 to a half, I kind of think of it that way, that we're allowing that air, we're allowing room for air in that top foot of soil if we've drained that water table about that 0.5 inches or a foot in the soil. Now, as we think about factors to consider in drainage design, there are a lot of factors to consider as we think about this. And on the right hand side, the blue box would be our drainage coefficient, and that would be looking at how big is our pipe, what's the grade of the pipe, and what's the pipe material. And essentially, that would be how thick, how quickly that drain can get the water out of the field. Okay. So once the water's in the pipe, how quickly can we get it out of the field? And we would, again, design that for about 3/8 to a half an inch. So that would be, again, drainage coefficient, how quickly we can get the water off out of the field based on the pipe size, pipe grade, pipe material. But then also a factor to consider is how fast we can get water to the pipe. And that would be what I would term and is kind of commonly referred to in the drainage area as drainage intensity. And that would be a function of how close the drains are spaced together. So the drain spacing, the depth of the drains, the saturated hydraulic conductivity, the depth to the restrictive layer. And for my colleague, Dr. Asan Agane at Michigan State, that's done some work on this, also a function of the pipe size and perforations of the pipe. So if we had a system with a low saturated hydraulic conductivity, to get the same drainage intensity, we would have to have the drains spaced closer together. One of the things that we want and really need to get the best investment out of our drainage system is for that drainage intensity, how fast water can get to the drains, to match with how fast we can take how fast we can take the water away with our drains, our drainage coefficient. And I'll talk a little bit more about this because I think oftentimes as I talk to farmers, they think about maybe pattern drainage in the field, that drainage intensity, and maybe don't think as much about the drainage coefficient or what pipe size we need to get that water away. So again, um, uh, uh, just terms again on the drainage intensity and drainage coefficient. The intensity is the drainage rate when the water table is at the surface midway between the tile lines, kind of how fast the water can get to that tile. The drainage coefficient would be the rate that the outlet works can remove water from the site. So how fast water is removed from the field. The top one would really, that intensity would depend on our soil properties, drain depth, spacing, and the depth to the restrictive layer, whereas the drainage coefficient is going to depend on the size of the pipe, slope of the pipe, and then the type of pipe that we have. That'd be where that hydraulic roughness of the lateral submains and mains may come into play. And as I said before, these need to match to get the best investment out of our drainage system. So here's a case, Northeast Iowa. Shortly after I started at Iowa State University, I went on a visit, and this individual was putting the drains in at about a 50-foot drain spacing. So the rate at which water could get to that drain was pretty quick. 50-foot drain spacing, good soils. This was probably 3.5 to 4 feet deep. And I asked this individual, what kind of main are you draining into? And I should have said this was draining about 100 acres. And they said, oh, it's a 6-inch main down in the bottom of the draw there. So they were draining about 100 acres into a 6-inch main, very intense drain spacing. So the drain spacing, I estimated 50 feet, drain depth 3 to 4 feet. The drainage intensity, we could get water to the drain in this situation at about 0.75 to 1 inch per day. So, and you'll note that's above kind of the standard that we would routinely design our drainage coefficient or the size of the pipe to be about 3/8 to a half, about double that. But I said that they had about 100 acres draining into it, 6-inch drainage main. I was kind of gave the benefit of the doubt and said we had a 1% slope. So you guys can think, what would be the drainage coefficient for that case? Less than 0.125 inches per day. So this system was designed that we could get water to the drain at 3/4 to 1 inch a day, but we could only take it out with the drainage main at about 0.125 inches per day or less. This would be a case where the drainage coefficient and the drainage intensity are not matching. Really, what should be done here is to put a bigger drainage main in. I asked this contractor, do you think that drainage main is big enough? And he said, oh, heck no, not even close. I said, well, did you talk to the landowner about that? Yeah, I certainly did. And they wouldn't pay for a bigger drainage main, even though we probably put $800 to $1,000 per acre in drains in the field. This individual didn't want to invest in putting a bigger drainage main in. I would argue they probably are not getting all the benefits from that intensively drained field because the main is way undersized. So again, that drainage intensity, 0.75 to 1 inch, drainage coefficient less than 0.125. The actual drainage rate from the field is really less than that 0.125 inches per day. So I bring this up just as if you're thinking about drainage, we need to think about both how fast we can get water to the drain as well as how fast we can take it away with the main, and those things need to match up a little better. Um, and as we think about then what drain spacing we should use, again, we want to try to match that ultimately what we have for the drainage coefficient. But some things to think about with drain spacing is that narrower is not always better. So this is Iowa conditions. I will grant that for these soils, but there's a range of drain spacing that maybe to maximize relative yield here. And we find that might be anywhere from 40 to 80 feet. However, if we think about that, the net annual return for that drainage system, there would also be a range to maximize that net return from the installation of the drainage system. And that's going to be a little wider because we're factoring in that cost of installing that drainage system. And in this case, maybe more like 60 to 110 feet for these soils. So versus 40 to 80, now we're 60 to 110. I bring this up, based on the objectives of the installation. If your objective is to maximize long-term benefit from a yield perspective, we probably need to go a little wider with our drain spacing. If it's to maximize, or to minimize excess water stress in a wet year, and minimize excess water stress in a wet year, we're probably going to go a little bit narrower. But if we go a little narrower, we need to make sure that we design that drainage outlet to accommodate that narrower drain spacing, higher drainage intensity. So one thing, if we do go a little bit wider, that may optimize our net return, but it also may, the research has shown it can reduce that drainage volume slightly, thereby reducing nitrate loss slightly. So what we found is that drain spacing has little impact on the concentration of nitrate we see coming out of the tile line, but if we can reduce the volume of water, we can reduce the nitrate loss from our drainage system and from our field. Okay, if you want to look more at some drainage tools, Michigan State University has some good drainage tools, and there's some information from Transforming Drainage. Both of these would have information about kind of based on if you estimated your soil type, looking at what drain spacing you might need to get a drainage intensity close to a half an inch. Also, it could help you with sizing of your drainage main to get that drainage coefficient to a 3/8 to a half an inch, excuse me. Very quickly, some of the things that we can do in our drain landscape to reduce some of that nitrate delivery. As I talked about earlier, our drainage systems can be a delivery mechanism of delivering nitrate to downstream water bodies, but there are a number of things that we can do to reduce that delivery of nitrate. One would be controlled drainage. We'd need pretty flat fields here, maybe 0.5% to 1% slope. But in this case, we're going to put control structures in to manage the water table back in the field. We don't need to have free drainage 24 hours a day, 7 days a week, 365 days a year. In the winter months, in the summer months, we might be able to put those uh, boards in the control structures in place and reduce some of the drainage outflow. And research across the Midwest has found that with controlled drainage, we might be able to reduce downstream drain flow 30 to 50%, maybe more in some cases. And what we found with that research is that we don't see a change in nitrate concentration, but because we're reducing the volume of drain flow, we're reducing downstream nitrate load about that same percent that we're reducing drain flow. I will not talk about bioreactors because I don't want to steal any of Margaret's thunder, but this would be a practice where we're going to route drainage water to try to promote denitrification. Another one that can be used in a lot of settings where we have drainage is a saturated buffer. In many of the cases where we have a buffer and we have tile drainage under existing conditions, that drainage is running right below the buffer. There's no treatment of that water as it's moving below the buffer because it's in that drain pipe. So what folks are looking at is, can we again put a control structure on the upstream edge of our buffer, put in a lateral tile line along the upstream edge of the buffer, and promote shallow groundwater flow below the buffer, promoting denitrification of the water and maybe plant uptake of nitrate. We found from research in Iowa, this can be very effective in reducing downstream nitrate delivery and pretty low cost. We're just paying, if we have a buffer there already, just the cost of the structure and that drainage pipe along the upstream edge of the buffer. Probably one of my favorites is kind of targeted wetland restoration or creation to treat drainage water from a large area. So this case, you can kind of see a landscape. This is an Iowa landscape, but we have row crop land, and we're going to intercept that water before it leaves the watershed. So we're going to collect all the subsurface flow and surface flow and route it through a wetland that you can see down on the kind of lower right hand side. And that wetland, this is an example of the type of nitrate removal wetland that is being installed in Iowa in many places. And this wetland, if I go back to the previous slide, sorry to jump around, if that wetland pool down at the bottom, so the blue area you see at the bottom, if that's about 1% of the contributing area, so about 1% of the total watershed area, long term, we would expect that to remove about 50% of the nitrate that it sees. We might have a little buffer around that wetland, so we might be taking 3 to 4% of the total landscape into wetland and surrounding buffer, and with it removing about 50% of the nitrate. As you look at this type of system, it's also going to provide a lot of other benefits that many in society appreciate: waterfowl habitat, wildlife habitat, pollinator habitat, monarch habitat, maybe in that buffer around there, as well as some aesthetic value. I grant beauty is in the eye of the beholder, but for many, there may be aesthetic value there. We can also think of wetlands near streams where maybe old oxbows. And so in many areas of Iowa, they're looking at oxbow restoration and making sure that we route that drainage water into that oxbow wetland to, again, promote denitrification. So saturated buffers, bioreactors, wetlands, and multi-purpose oxbows. The primary removal mechanism of that nitrate is going to be denitrification of the water as it moves through this system, microbial denitrification. So we're converting that nitrate primarily to dinitrogen gas. As we look at all of these practices, they're removing a lot of nitrate per contributing area. So anywhere from 2 pounds per treated acre to 11 pounds per treated acre for a wetland. And one last practice in my last minute that we're looking at within the drained landscape is drainage water recycling. Can we capture drainage water that would otherwise export water and nutrients downstream store it, and reuse it in the field for supplemental irrigation. We found that in many areas that may help us enhance crop production, but the real question now is there enough crop production benefit to offset the increased cost and management of this type of system? So kind of be on the lookout for more research on this topic into the future. So with that, I think my 20 minutes are up, and so I can turn it back to Laura to introduce um, Margaret.
Yes, thank you very much. Yeah, thanks for starting off the conversation today with tile drainage. It's some great information coming from Iowa. So, as we transition to Dr. Zimmer, we are going to launch a demographic poll. This anonymous information just helps us evaluate our audience. So, reaching with, who are we reaching with this type of work? So, if you don't mind filling out the poll. Where I see, yep, Dr. Zimmer's, yep, that looks great, Margaret. We'll just give a maybe 30 seconds for everyone to fill out this poll. All right, great. I'd love to introduce our next speaker, Dr. Margaret Zimmer. Dr. Zimmer is a watershed hydrologist and associate professor in the Soil and Environmental Sciences Department at UW-Madison. She studies how and why water moves throughout Earth's surface and near surface environments. Today, she will be focusing on bioreactors. So excited to hear some specific data she has from bioreactors within Wisconsin. Take it away, Dr. Zimmer. That looks great.
Okay, great. Thank you so much, Laura. And thank you all so much for this opportunity to speak with you today. The work I'm going to talk about was done in collaboration with some colleagues at the U.S. Geological Survey Upper Midwest Water Science Center. So I'll be talking about some edge of field bioreactor monitoring that we've collaborated on over the last 6 years. And of course, special shout out to Dr. Matt Helmers for introducing all of these wonderful concepts of conservation practices like bioreactors, but I also appreciated that he resisted the urge to steal my thunder specific to bioreactors. So, as Dr. Helmers mentioned, tile drainage infrastructure is widespread across the Midwest. I love this map, which shows portions of the Midwest that has tile drainage. So, the blue represents 30-meter or about 100-foot pixels that have tile drains. In Wisconsin, most of our tile drainage is on the eastern portion of the state, but with an intensifying water cycle and weather events, there may be need for putting in tile drainage in other places that maybe traditionally didn't need it. I think today about 10% of cropland in Wisconsin has tile drains installed. So to reiterate a little bit about what Dr. Helmers introduced in his presentation, so tile drains are installed in soil to help drain water from fields. This is a very productive practice that essentially introduces a highway for water to drain from. And it promotes crop growth by aerating the soil. It also provides more unsaturated soil zone for root growth. This practice also increases the direct connection to our waterways. And so with this, water can come from our landscapes, from our agricultural fields into our adjacent waterways and bring with it sediment from the landscape as well as nutrients from fertilizers that have been applied to the land. When concentrations of nutrients are too high, they can produce adverse environmental effects like algal blooms, for example, that can make water unsafe for recreation as well as for human and aquatic life. So, edge of field bioreactors are great because they can reduce that agricultural nutrient contribution to our waterways. Essentially, they are big pits of carbon, like usually we use wood chips, where nutrient-laden tile drainage can be funneled to. So if the bioreactor receives too much drainage, some of that will bypass but then the majority of water will be directed to the bioreactor. And so these bioreactors, as I mentioned, have these high carbon content, and that essentially fuels microbial activity. There's also relatively low oxygen conditions in these saturated wood chip piles. So nitrate can be removed and it will be outgassed to the atmosphere as harmless N2 from the denitrification process. This means that overall there are less nutrients going into our waterways. And also I should note that studies have shown that bioreactors promote not just the reduction of nitrate, which is what they're designed to do, but they also reduce other materials like phosphorus or sediment from that agricultural tile drains. So there are design standards that are set by the USDA Natural Resources Conservation Service. So this means essentially that bioreactors are designed in a way where they target treating at least 60% of the annual flow of the annual tile drainage. That they're also designed to reduce annually about 30% of the nitrate load that they receive. And that they are designed in a way that the bioreactor system itself can last for about 10 years. But it's not free to install a bioreactor on your farm field. So given this high cost of bioreactor installation, of course, we should be concerned about their longevity through time or their performance through time, or to make sure that they are appropriately sized for your agricultural drainage. So with those design standards in mind, the study that we developed that I'll talk to you today is really targeting two knowledge gaps that we have. So first, bioreactors are designed to promote denitrification via microbial activity. And it turns out microbes do a lot better in warmer environments. And so there's concern regarding how bioreactors might perform in northern regions of the United States, where it can be cold for a significant portion of the year. And then the second knowledge gap that we're interested in is thinking about as our water cycle intensifies, and we're already seeing more intense precipitation events, and we're already seeing more rain and less snow. There's concern about how current design standards for bioreactors might influence bioreactors' abilities to treat incoming water when our storm events are more intense. So with those two knowledge gaps in mind, we set out to assess an edge-of-field bioreactor over a 6-year period to understand its performance through time with focus on annual, seasonal, and event scale nitrate removal. So the bioreactor that we studied is in southern Door County. We monitored it from 2019 to the 2024 water year. So that's October to October. For this particular field that drained this bioreactor, the farmer grew alfalfa for the first 3 years and then switched to corn in our 4th year of study, and then had corn on the farm field in the last 2 years. And no tillage occurred during our study period. I just want to note the picture on the left is a picture of the bioreactor when it was just built, and then the aerial image on the right designates where the bioreactor is, and then the black line designates the contributing area upslope of that bioreactor, and then those gray lines represent the actual tile drainage feeding the bioreactor. Okay, so this bioreactor, as I mentioned, they're essentially pits in the ground, and so they're lined with, or this one is lined with a 4mm polyethylene lining, and that's supposed to limit any loss or exchange of water in the subsurface. There's a mix of tree species as the wood chip materials. Specifically, we used hickory, ash, and aspen. We monitored water flowing into the bioreactor and out of the bioreactor as well as water that was funneled around the bioreactor in like really high flow periods. We also monitored the temperature within the bioreactor at 3 different depths because we were interested in the environmental conditions of the bioreactor and how it may influence its functionality. We also had a camera at the site, which allowed us to assess if there are any overtopping events, or we could also monitor what was happening on the field. We collected almost 500 water samples at the inlet and the outlet of this bioreactor over our 6-year period. So we have a lot of data to help us understand how the bioreactor is functioning. So now I want to show you some of our results. So to begin, I want to provide some climate context for our 6 study years. What I'm showing you here is the total annual precipitation. It varied between about 29 and 46 inches. The first 2 years were quite wet, and the last 4 years were slightly drier. Now I'm going to overlay the percent, a black line that represents the percent of incoming tile drainage that was treated by the bioreactor. So anything not treated by the bioreactor means it bypassed the bioreactor. Most likely because the bioreactor was like at capacity or it was full of water, and so it just couldn't take on any more water. And so now I'm adding a red horizontal line at about 60%. So that's that NRCS design standard that we are shooting for. So ideally, this bioreactor is designed in a way that it can treat 60% of annual flow. And we met that goal in all but 1 year. And interestingly enough, that year was the year that we had the least amount of precipitation. So that suggests that the bioreactor maybe wasn't necessarily getting overly inundated with water. Instead, we actually think maybe a pipe got temporarily clogged, maybe with sediment in 2023, causing this loss of water being able to actually enter the bioreactor. Okay, so now I also want to show you how many kilograms of nitrate was in the tile drainage that was being funneled to the bioreactor. So the blue bars are the total nitrate load that we measured in the inlet and the bypass pipes. And then the black line is just what nitrate actually made it into the bioreactor. And so again, that difference between the top of the blue bar and the black line is our bypass. So the nitrate load that was in our bypass. So you can see the first about 3 years, we have about under 250-ish kilograms. And then in 2022, we see a big increase in our nitrate load. And that coincides with a switch from alfalfa to corn on the farm field that's contributing tile drainage. Also, you'll see in 2023, due to that, what we think is that a clog in the pipe, we treated a little less than half of the nitrate load. All right, next I want to introduce removal efficiency and total reduction. So removal efficiency is essentially dividing what comes out of the bioreactor by what comes into the bioreactor. So that's essentially how efficient the bioreactor is at removing nitrate. And that's the blue line on this graph. The total reduction takes into account what the nitrate load is in both the bypass and the inlet. So to remind you, the NRCS design standard is specific to the bioreactor functionality, where bioreactors are in theory designed to treat about 30% of annual nitrate load. So to help you visualize that, I added a red line at 30%. So we see that the bioreactor met this design standard in 2 of the 6 years. So essentially when the blue line is above the red line. That said, in year 1 and year 4, we were pretty close to that 30%, maybe even within a measurement error. And the reason the total reduction is so much lower, especially in those last couple years, is because a significant portion of that nitrate load was bypassing the bioreactor. So what caused the lower than designed removal efficiency? Well, we think there might be a few reasons. First off, nitrate removal rates in the bioreactor were quite variable. So I'm showing nitrate removal rates in the bottom right plot through time. They didn't necessarily decrease over the study period, but there was a pretty big dip in the removal rates, especially in 2022. Let's see, I think, yeah, there we go. So I'm highlighting that dip in 2022. And so that reduction in nitrate removal rates coincides with our removal efficiency decrease. And then in addition, I showed you that nitrate load plot before. That's that top right plot. And just to remind you, we saw quite a big increase in nitrate load in our tile drainage when we switched from alfalfa to corn. And so that just means the system is being inundated with nitrate, potentially to the point that it has too much nitrate to process efficiently. And so it's essentially hit its or exceeded its max. Okay, I also just want to note that we calculated the difference between water measured at the inlet and the outlet of our bioreactor. And in the first 4 years, the difference was 11% or less, which is great. That means that there's very little difference between how much water is coming in and how much we're measuring coming out. And we attributed any differences to maybe a little bit of leakage or evaporation, or maybe even just measurement error. However, in the last 2 years, we observed a very big difference in water coming in versus coming out. We actually saw a huge decrease in water coming out. And so we think that there may be leakage in the bioreactor. So whatever clogging that we also observed in 2023 may have created a step change or a shift in the bioreactor functionality. Maybe it caused a big leakage to start, and that has moved or like perpetuated into the year 2024 as well. Okay, so now I just want to take a moment to look at seasonal dynamics. So what I was showing you before was at the annual scale. So now what we are looking at is the nitrate load, but for each year, but broken up by season. And I'm first showing you winter. So the total height of each one of those bars is the total nitrate load. The gray bar, the gray portion, is the portion that bypassed the bioreactor. The blue part is the portion of the total nitrate that entered the bioreactor but was removed via denitrification. And then the red part is what entered the bioreactor but just moved through it and discharged to the adjacent agricultural ditch. So on average in winter, we saw about a 32% annual nitrate load coming through. We can also look at spring, summer, and fall. And here we see that winter and spring have the most nitrate load, summer sees the least. And we see that since most of our loading is occurring in winter and spring, that's also when we have the most bypass. We can also look at how the seasonality affects removal efficiency and then those actual nitrate removal rates. So just to remind you, for our annual scale, we want a 30% removal efficiency. We see that also at the spring and fall seasons, not quite in winter. And then we see a negative removal efficiency in summer. And I think that's because there's just not a lot of nitrate entering. So when you have really small numbers, when you divide them, they can make really big numbers. Also, it could suggest that nitrate is being produced in summer. Interestingly enough, we also saw the lowest nitrate removal rates in summer, and that's surprising because that's the warmest time of year when it's biologically most favorable to remove nitrate. So again, that might be driven by there just not being a lot of nitrate loading or the fact that there might be nitrate production occurring. And then lastly, I just want to note that we can calculate total reduction. So again, that takes into account the bypass, and across the board, our removal efficiency decreases again because now you're taking into account what's bypassed. Okay, and then I just want to end in my last couple of minutes to talk about some event delineation that we did. So now we went from annual to seasonal, and now we're going to just look at precipitation events. So we can delineate events based on our measuring of the water flow into the bioreactor. So this is an example of us monitoring the water level coming into the bioreactor for a random day in August of 2019. And you can delineate the event based on when there's water starting and when it ends. And so we did that. We went through the entire time series and identified about 38 individual events across the 2019 through 2022 years. We didn't choose the last few years because of that weird leakage that we're observing. So it's much harder to do the math when you have leaking. And we ran a multiple linear regression to identify what we thought, to identify potential drivers of nitrate removal. And so what we're looking at here are the event-based nitrate removal for each season for each year. And so the box plots essentially just aggregate all the individual events for that season. If you were to take all those box plots and average them together for each season, you would see that there is not a difference between nitrate removal rates by season. That's very surprising because the air temperature is very different between winter and summer, but statistically, the removal rates are the same. We did see a couple elevated rates, specifically in winter 2021 and fall 2021, and those occurred in events that happened after prolonged dry periods and probably after fertilizer was applied. And so I mentioned we did a multiple linear regression to explore what drove these. And in that regression, we identified that the nitrate concentration of the inlet water, as well as the bioreactor temperature, were the two most important drivers. And I'll highlight a couple reasons why that makes sense. So I have highlighted some seasons that had the highest nitrate removal rates. And then I've also highlighted the seasons that had the highest nitrate concentration in our inlet water. And you see that they correspond to each other. Similarly, I've highlighted some periods where we have a little bit elevated nitrate removal rates in the seasons, and those are also times where we have elevated temperature. Okay, so to conclude, some takeaways. On an annual and a seasonal timescale, we saw that our bioreactor function generally met our target of 60% flow treatment and 30% nitrate reduction. But we did see signs of leakage after the fourth year. We also saw that spring and winter showed the highest nitrate loading, also the highest removal rates, and the overall highest efficiency. But those were also periods where we have these really big events. We had the highest bypass flow, and that made our overall total reductions the lowest. On event timescales, we showed that individual events have pretty variable nitrate removal rates. When you aggregate together, there are no differences, but when you look at individual events, you see that the timing of fertilizer application makes a big difference for how much loading we have and then how much removal we have. And then also nitrate concentrations and bioreactor temperature are the most important drivers. So for implications, this study helped confirm that the crop type and the fertilizer use plays a very important role in total bioreactor reductions. If you inundate the system with too much nitrate, it will hit its max capacity. Also, bioreactors are a great conservation practice for removing nitrate from agricultural tile drainage, but we have to be careful in terms of how we size them and how we consider their functionality, especially when we're thinking of the future and in terms of the increasing intensity and magnitude of precipitation events. And with that, I'll thank you very much.
Great. Thank you so much, Dr. Zimmer. I really appreciate the conversation and the two presentations. It was so nice to have Dr. Helmers start kind of more broad considerations, some, best management practices to include, and then really diving into one of those, the bioreactor, to see just how well it really does perform on Wisconsin farms. So really nice to have both here. We're getting some great Q&A, some great questions in the Q&A box. So please feel free to keep adding your questions in. I can try to, let's see, I see Dr. Helmers is asking or answering a few of them. So I guess I'll just quickly, because I'm going to make sure people can see the answers. We had a question that was, what happens when it drains into an undersized main? So when Dr. Helmers was talking about that drainage intensity not equaling the drainage coefficient, what would happen? And so Dr. Helmer said, yes, you could get more soil wetness in that circumstance and perhaps even ponding, depending how much rainfall you get. So you may want to make sure those, when planning it out, all those numbers work out. So and then there was another question about saturated buffers. How does that flow work within a saturated buffer? And so Dr. Helmers answered there's a control structure installed that raises the water table. And so that water can sit there. And then so a lateral is placed in the drain depth, and that lateral would then be installed on the flow grade. So you can control using that control structure how the water moves within that saturated buffer. Okay,
Laura,
oh, go ahead. Yep.
I'll answer, I guess, go to one question there. There was kind of, I'll let Margaret maybe answer on the, kind of situations where it shouldn't bother installing a
Yep.
bioreactor, but there was one about tile drainage in general, and that's a great question. Not every field, not every soil are you going to see benefits from tile drainage. So I think one of the really important aspects is to understand whether you have a naturally poorly drained soil that could benefit from tile drainage and where you could effectively put that in. I think I see some fields in Iowa at times that they may not have high water table conditions, so I'm not sure they're going to really benefit from that tile drainage because if that water can move below the drain line, you're probably not going to get much water in that drain line, and you're not going to see much benefit from a crop production standpoint.
Okay, great. Great. And then yeah, I guess part two to that same question for you, Margaret, is there a situation where you shouldn't bother installing a bioreactor other than just finance? Say like finances isn't the issue, what landscape perhaps would it not work in?
That's a great question. I also am very curious what Dr. Helmers thinks about that, but I mean, I personally can't think of a scenario in which you would not want to install a bioreactor if you have tile drainage that has high nitrate concentrations. I personally do not see a reason not to.
Yep, I would agree with that. And I think one of your points, Dr. Zimmer, was spot on that if you have a drain that's high in nitrate, I could envision that somebody maybe, and is doing a lot with cover crops or crop rotations and maybe has pretty low nitrates to begin with. So then we might want to look at other fields. I guess one caveat on some of that is, I've gotten questions a couple times about, in Iowa, we have some tile intake terraces, and people be like, oh, should I put a bioreactor on that because there's tile? Well, that's collecting surface runoff rather than drain flow. And you may be getting a lot of sediment in there that could plug up the bioreactor. So that's, maybe one area that if you had a lot of surface intakes in your field, you might want to be pretty cautious with a bioreactor because you may get some sediment in there that could plug it up.
Thanks.
Yeah,
Great,
and
thank you.
definitely in the aerial image that I showed for our like site information, the contributing area was actually maybe double the size of just where we're getting tile drainage too. So yeah, definitely thinking about where your water can be coming from and like what's going to be in that water could play a role.
Great, awesome. A question here on a lift barrel or lift stations in general, I know is a hot topic in Wisconsin. Do those help slow nitrate losses, reduce losses?
So I've always thought of that the lift stations you could almost um, operate them like controlled drainage systems that in certain times of the year you don't pump as much, and so in that way we may be able to reduce some of the drainage volume compared to if we just pumped 24 hours a day, 7 days a week, 365 days a year.
Okay, great. Thank you. Margaret, I'll ask you this question. Can you just, you talked about the design standard. So a question here was just having the right number of to like target total reduction. So NRCS you said was, a target goal of 30% reduction, but you also mentioned a 60. Can you just confirm kind of when you're, drawing up the design standard, what target goal do you have?
So I see the question. So yeah, to clarify, so I think one consideration is like how big do you make the bioreactor? So how much water can it actually take on? And so one design standard is that you want to make sure that the bioreactor size so that it can treat or essentially funnel 60% of that tile drained water through the bioreactor. And then the other consideration is what the bioreactor actually does with that water. And so the other then design standard is making sure that you have the right environmental conditions within the bioreactor, so the carbon source that can allow denitrification to occur, which is essentially the removal of nitrate or conversion of nitrate to N2 gas. And so that is that 30% nitrate removal. I see that question. So they're saying, is 60 times 30, does that equate to an 18% reduction in nitrogen pollution? That's a great question. I don't remember actually seeing in the design standard like protocol talking about a like total reduction in that sort of way. And in fact, I would encourage you to think about them quite separately. Again, maybe Dr. Helmers has thoughts on this as well, but I would definitely think about how the capacity of your system for maintaining and treating water, and then also the functionality of it as well. So those are kind of two separate things.
Great, thank you. Just I guess maybe a quick question about what does a bioreactor cost? Do you have a price point?
Ooh, that's a great question. Um, I don't know because I think it would depend on
Probably
how
depends
big
on
it
how
is,
big.
where you're sourcing the materials from, if you have equipment on hand to dig a
Okay,
hole.
sure.
Um,
Contractor fees.
I,
Yep.
Yep. I would say they would probably be less expensive for the materials in Wisconsin than Iowa because wood chips are not as easy to come by in Iowa as they probably would be in Wisconsin. That ends up being a pretty big part of the cost here. And actually, there's some work looking at using corn cobs instead of wood chips. There's also some work. Dr. Billy Beck here at Iowa State is looking at kind of different tree species and which ones may work the best.
Great. Great. You actually answered another question on there, so
Okay.
thanks. Perfect.
Yeah. And
Uh,
corn cobs do work fairly well. We're still looking at kind of how long they last. Or on that week. Dr. Michelle Sapir is looking at that.
nice. Awesome. If the bioreactor is failing or leaking, like you said, Margaret, at year 4, you thought about some leakage. How do you fix that? Do you have to kind of dig everything out and start over, or what would you do?
That would be my recommendation. If you know that there is a substantial shift in the functionality of your system, I would probably try and investigate what's causing that. In our case, we're very lucky that we are monitoring the water flowing in and out of the bioreactor, and so we can pretty much identify that there's probably a leak, there's definitely a leakage occurring. And so what I would say in that case is dig out the wood chips, look at the liner, see where the leak is, and then either replace the liner or repair it. You also then have an opportunity to either put the material back in or replace it with fresh wood chips, which could also then prolong the viability of your system.
Great. Thank you. Would it be worth pairing like a bioreactor with some other practices too? So we see, we're not, sometimes the bioreactor depends what the efficiency is. What else could you pair with it or should you pair with it?
Eric, thanks for that question. It's good to see you again. We spent a lot of time working together on the Iowa nutrient reduction strategy many years ago. And so I guess if I give my answers, we're going to need it all. And so, I think it starts with good infield nutrient management. We need to think about, our cropping systems and how we can reduce that nitrate leaching at the source. But then, incorporating some of these edge of field practices to kind of treat that. I think one thing to note is that an area that might work for a saturated buffer or a bioreactor, may not be conducive to a wetland. So, it'd probably be rare that you have a specific field where a bioreactor, saturated buffer, and wetland would work. So, I think every landscape's going to be a little different. And even if we implement these practices that doesn't take away the real need to look at good nutrient management in the field and our cropping systems to try to reduce that nitrate leaching.
Great, thank you. And maybe two last quick questions for you, Margaret. Does the number of days with flow affect efficiency within the bioreactor? This person said they could flow for all year round. Would that reduce efficiency?
Yeah, that's a great question. Um, I think as long as you have a carbon source and microbes to do what they do best, your bioreactor should function appropriately, regardless of how long it's flowing.
Great. And then last question for you, Margaret. Are these results available online if someone wanted to look more into, the nitty-gritty of your study?
Hopefully, eventually. So this
Okay,
paper is in review right now for publication in a scientific journal. So it will be published and will be open access and available to the public,
great.
hopefully this year.
Was phosphorus measured too?
Yes, we also measured several other constituents in the water, sediment and phosphorus as well.
Interesting. Great. All right, well, I want to make sure we kind of stay on time, but thank you. I want to thank you guys both for being here. That was really great discussion. We had a lot of questions, so I know everyone on the call today was very interested too. Tile is becoming quite the hot topic in Wisconsin now. So you can see here CCA credit if you scan that QR code or type your CCA number in the chat. We will get those for you. And as you exit today, or I think the poll just popped up. We are asking two questions just again to make sure we're doing our job and seeing how you enjoyed this webinar and what you learned. So I want to thank you all again for joining us today. And we are hosting a webinar every Tuesday in the month of February and March, noon on Tuesdays, every Tuesday this year. So I also want to give a little plug to this. We're hosting a drainage workshop this year in March 9th in Marshfield. So some highlights there. If you see on your screen, those lift stations, as I mentioned, are becoming a hot topic. So we are talking about those, bringing someone in from Minnesota. So that's a 1-day workshop we are offering. And again, yes, this thank you to everyone. Please reach out with any questions, concerns, and these here are the next webinar series. Next week is another featured talk from that Wisconsin Water and Soil Health Conference. I will be presenting my work again, so you don't want to miss it on phosphorus. Thank you all.